Hi, this is Anna Douglas with the first video of the module Polarization Optics for the course ECE 513 Intro to Optics and Photonics. In this video, we're going to understand that the polarization is related with the orientation of the electric field. We're going to introduce a couple of applications for polarization. We're going to show you the different type of polarization states, and we're going to do a in-class problem, or we're going to revisit an example to determine the polarization state given an electric field. Then we're going to introduce the Poincare sphere as a representation of any polarization state. And then we are moving to define natural light and understand the working principle of linear polarizers and see how much light is transmitted after a linear polarizer or a cascade of linear polarizers based on the orientation of their transmission axis. So polarization optics has so many applications. Probably one of the most important one is in photography. As we can see, we can try to reduce some glaring. So here when we use a camera with a polarizer, then we can see what is under the water. We can improve contrast. We can kind of see better the colors. But also for material, especially for plastics or glasses, we can if we put them within two linear polarizers that they are orthogonal each other, we can analyze the stress. It has also application or astrophysics or chemical. Most importantly, or based for my research, it's really important, the polarization for analyzing tissue. So it can be used as a screening or diagnosis because we can see the polarimetry characteristics of the samples. So we come from working module 5, right? So module 5 is the one that we were discussing the electromagnetic field theory, and we were at the end saying that we always have an electric field and a magnetic field that they are coupled each other and they are perpendicular to the polarization, but we always have these two fields that they are coupled. So now when we are studying module 6 is gonna be focused on the polarization, which is just thinking about our electric field, and the polarization state is gonna be defined as the relationship between the X and Y component in the electric field. So we have here our transverse electromagnetic field, and we are thinking about the electric field, and we are saying that is the real part of a complex amplitude. And here we have this is gonna be our monochromatic wave, right? And then here we have our plane wave propagating along the Z direction. So we are thinking that our electric field, which is gonna depend on our transverse or spatial coordinates at the time, coming right as initial vector, and then we're gonna have the real part of the complex exponential. We can write it as our cosine, and then we're gonna have here our X component, and we're gonna have our Y component, where our X component is gonna be some amplitude, and then here our cosine is gonna be omega t minus k c plus some initial phase along the x component, and we're gonna have similar, in general, the amplitude and the phase of the y component might be different with respect to the x component. So in general, our a sub 0 x is gonna be different to a sub 0 y, and also the phase between both components is different, but both components are gonna be periodic functions with respect to the time and the distance. So we were saying that we have our electric field expressed in terms of the in Cartesian coordinates along the x and the y, and we are already saying here that in general both amplitudes, both components gonna have different amplitude, they're gonna have a phase difference between them. So we're gonna define the phase difference as the difference between the phase of the y component minus the x component, and let's consider that if the phase difference is equal to 0, which that means that both components are equally delayed, the cosine values are going to be the same. So we can have here our x, the amplitude along the x and y component are going to be different, but we're going to have the same change is going to happen with respect to time. And just going to say here in general phi of x. So here what we know is the amplitude of E oscillates sinusoidally in time and C, and then we can define like the angle of that change as theta, with the inverse gonna be the inverse of the tangent of r as the amplitude of the x component versus the y component. So, and this is what is showing us here, right? So here is showing that we have some direction, right? And the direction does not change, but through that direction, what we're gonna keep changing is the amplitude of the components. So in general, I want you to think that when we are talking about linearly polarized light, we need to know that the angle between the x and y components does not change, that it's kept invariant through the propagation, but what it changes is their amplitudes. That is something that is gonna be changing through the propagation. So let us consider a case where the phase difference, remember that is the phase of the y component over the x, that's gonna be a odd multiple of pi. So m is an integer and the phase difference is gonna be an odd multiple of pi. So for simplicity, we can consider that the phase of the x component is 0, and we're gonna assume that the m equals 0, it's a value, so then the y component is gonna be pi, right? So we have our electric field that we can write here our xy components. So it's gonna be cosine of omega t minus kc plus our y component with the amplitude, and then here we're gonna have cosine of omega t minus kc plus pi. And this cosine, if we decouple, that is the same as say cosine of omega t minus kc with negative sign. So our electric field is gonna have the x component with amplitude a sub 0 x, and then the y component with negative amplitude, and then our cosine that's gonna be dependent on the time and the distance. So we can define here the tangent to define the angle. The tangent of theta, that's gonna be our s component minus our y component, the amplitude. And that, if we assume that both components, they have the same amplitude, that is gonna be equal to 1. So that means that we have here like a minus 45 degrees. The other case is when the degree is 45. So that's gonna happen when the phase difference is gonna be a multiple of 2 pi. And in this case, our electric field, we're gonna have the same amplitude for the x and y component, but now we, instead of having a subtraction, we have a summation with them. Sorry, and this is a minus. The other case of type of polarization that we might find is the circular polarized light. So we have considered that for simplification, that the initial phase along the x component is 0, so the phase difference is equal to the phase difference along the y direction, and we have our electric field with expressed in terms of the the x and the y component. So for the circularly polarized light, we know that both components, the x and the y component of the electric field, have the same amplitude. So that means, oh, sorry, that's a little mess. I'm combining two words. So they have the same amplitude. So that means that E sub 0 x, that's gonna be equal to E sub 0 y. And we can consider the case where the phase difference is a multiple of minus pi over m. So this is gonna be the case where my y component is gonna lead the x component by pi over half. So here my x component, right? I'm assuming that we have our same amplitude cosine of omega t minus kc. This is my x component, and now my y component, this is gonna be my same amplitude, but because I have here our pi and a half, this is gonna become, is the y component change with the sine versus with the cosine. So definitely the amplitude of the E field for through the propagation is gonna be the same, it's gonna be constant. And that means that the E field follow, or the end of the E field follows a circle. That's why we are saying that this is circularly polarized, because through the propagation the magnitude of the electric field is always the same, it's constant. But what we're gonna keep changing is the propagation angle. So we always gonna be moving through a circle, same amplitude, but we change the direction, how the electric field rotates. So as in other examples in nature, the direction matters. So we can find that the electric field the polarization is circular, but we can define the right hand circular polarization if the electric field rotates clockwise, or we can define the left hand circular polarization when the electric field rotates counterclockwise. At the end, the phase difference is gonna be the same, it's half pi, but it's gonna change the sign of the phase difference. And that's gonna mean that either the y component is leading the x component, or the y component lags the x component. The linear polarized and the circular polarized light are particular cases of an elliptical polarized light. Elliptical polarized light means that the electric field rotates and changes its magnitude through propagation. So that means that our electric field, and again, for simplification, the phase for the x component is 0, so the phase difference is just kind of like the phase of the y component. It's gonna have a x component with its amplitude changing, and then we're gonna have our y component that is gonna be having a delay with respect our s component, and in general it's gonna have different phase. And the relationship is that the end point of the electric field is gonna follow an ellipse. Cosine of phi is equal 1 the square root of 1 minus a ex is a 0x square sine of phi. So that means that the electric field and when I think about the electric field, it's just like the end of the arrow, the end point of the electric field follows an ellipse, and this is the equation of the ellipse. So let's do a simple example where we know our electric field. So here we have our X component and we have here our Y component. We know here what it's gonna be. This is gonna be my X amplitude, this is gonna be my Y amplitude, but we know that both of them are the same. So it's E sub 0, so then, and that means that R, which is this value right here, that's gonna be equal to 1. The phase difference, the phase of the X component is 0, so the phase difference is gonna be by half of pi. So that means that when we are putting here that the phase difference is 90 degrees, the cosine is gonna be 0. So that's gonna define our tangent of 2 pi, that's gonna be 0. So that means that our sine is equal to 0. And then here what we're gonna define is, like, again, when we put our phase difference, pi over 2, sine of 90 is 1, and here we're gonna have 2 over 2, so that's gonna be 1. So the angle to G, that's gonna be 90 degrees. And at the end, you're gonna find that that's gonna be defining our circular linear polarization, because we are putting everything right here. That's what we are. We are in the North Pole. So just as a summary of what you need to know is, the polarization tells you how the electric field rotates and changes through the propagation. The most general case is when we have elliptically polarized light. That means that the electric field rotates and changes its magnitude. Circularly polarized light, we know that the electric field rotates, but there is no change of its magnitude. And based if it's clockwise or counterclockwise, we're gonna define the right hand or the left hand circular polarized light. And the linear polarization light is when the magnitude changes, but the direction of the rotation, it's gonna be the same. In general, we can define any polarization state as the representation of two orthogonal polarization states. So it could be left or right circular polarization state, it can be horizontal and vertical linear polarization state, or any one that they are orthogonal with each other. Okay, so let's talk a little more, or let's go into what is a linear polarizer and how they work. But before going there, we need to define natural light. And you're gonna see natural light, or you're gonna see the term unpolarized light. So that means light coming from the sun or any incandescent or fluorescent or even LEDs, that they emit light with orientation of the electric field that is random in space and time. So there is no way of having a specific, the polarization state does not keep constant, and we can always express as the superposition of two equal amplitude incoherent orthogonal linear polarizer states. So what's gonna happen? So you have a natural light, right? That you have an electric field that keeps rotating across the direction, and it's going through a linear polarizer. Yeah, every time that you define a linear polarizer, you need to define, and I'm gonna try to be here, but you're gonna define its transmission axis. So linear polarizers are defined by the transmission axis, and they are elements that what they do is they change the polarization state of the incident light. How they change the polarization state? So when polarized light is when light going through a linear polarizer, after the linear polarizer, we find linear polarized light where axis is parallel to the transmission axis. So you see here you have natural light, you have here natural light that goes to a vertically linear polarizer. And now what you have after that one is a vertical. So now you have another linear polarizer. Now let's say that you have 45 degrees. So remember that this linear polarization, so that state you're gonna put it now in terms of the one, that should be straight, but you're gonna put it now here as one that is parallel to the transmission axis and one that is perpendicular. And only after the polarizer, we are only keeping the one parallel to the transmission axis. And again, that one now goes to the new one of the transmission axis and then the 90 degree. And you always keep the one that is parallel to the transmission axis. And this is what is the case. So linear polarizers can be used in cascade, and it's important because they can block completely light. So you have two linear polarizers where the transmission axes are parallel, so you are not losing any light. You're gonna have the same light after, and you're gonna have vertical polarization state. But if you have two linear polarizers where the transmission axes are orthogonal, you're gonna lose for completely your light. And you're gonna have a combination of them. How are we gonna know how much light is passing through a linear polarizer? Well, for that we use the Malus law. The Malus law tells us how much light is transmitted through a linear polarizer based on the angle between the incident polarization state and the transmission axis of the linear polarizer. The caveat here is that when you have unpolarized or natural light, then after a linear polarizer, you're always gonna have half. And now here from that linear polarized, which in this case is vertical, versus this angle, you're just gonna have the angle with them. So let's do a couple of examples. So let's assume that we have ordinary tungsten bolt. So that means that this is natural light. So this is just a type of light source, but this is gonna be natural light. So you have here natural light, right? So remember, you have all the possible polarization states. And your initial amount is gonna be 250 volts over meter square. And now that go to a linear polarizer that a priori we don't know where it's gonna be the angle. But it doesn't matter because every time the natural light goes through a linear polarizer, we're gonna have half of it. So that's gonna be 125 volts over meters square. So the next example is when we have linearly polarized light, and we know that it's perpendicular. So we have linear polarized light at 90 degrees. And incident and it goes to a linear polarized light with the transmission axis is also perpendicular. So we know that transmission axis goes to 90 degrees. So we have linear polarized light going through a vertical linear polarizer. So the angle between both is 0. So we're gonna keep completely the same intensity. We are not losing because they are completely parallel. The other case is when we have natural light. So we have here 500 volts over meters square, and we go through two consecutive linear polarizers. And this is gonna be the first linear polarizer at theta 1, and we have here the second linear polarizer at theta 2. So right here we know that we're gonna have half of it of the initial one, so that means that we're gonna have 250. Which direction, whatever is gonna be the direction of the first linear polarizer. And now I don't need to know the absolute values, but I know that there is 40 degrees apart. So that means that here my output is gonna be where I have before the second polarizer, cosine square of 40 degrees. And I don't have that number, but and then you just say what it's the incident, that's gonna be already 250. Or even better, maybe you can put it as terms of the incident. So you have the incident 1 over 2 cosine square of 40. So something that is a little silly, but just make sure that when you are estimating the cosine, you have your calculator with degrees. Because if you try your calculator it's in radians, then the values are going to be completely different and wrong. The last example is when you have here linear polarized at 40 degrees with respect to the vertical with a initial output, and then you have a linear polarizer set up at 20 degrees. So here you're gonna have linear polarizer like with the transmission axis is gonna be at 20. The angle between the polarizer and the input line is 20. So here your intensity is gonna be your initial one cosine square of 20 degrees. And now that goes to a second linear polarizer where the transmission axis is set up at 45 degrees. So at the output, you're gonna have linear polarizer lie at 45 degrees. The total intensity we are applying Malus law, so is what you have in front, cosine square of what is the angle. So you have 20 before, and now you are setting everything at 45, so it's a difference of 25 degrees. And then you can say, all right, but I know what before I had was my input cosine square of 20 multiplied by cosine square of 25. So that's gonna be around 0.725 your initial light. So you are kind of keeping around 72.5% during linear polarizer. So I hope that you have fun learning what type of polarization stage you have and how to apply the Malus law. Thank you.